This is part 2 of the AQA A-Level Chemistry Atomic Structure topic walkthrough. First section, we looked at electron configurations, we looked at isoelectronic species, different ways of writing out electron configurations. In part 2, we're going to take a look at first ionization enthalpy, and in part 3, we will move on to look at mass spectrometry. So, in the first instance, there are one or two things to just pause on, see what you can do, that check your knowledge from the video part 1. We have got here 4 different elements. We want to know the electron configurations for each of them in long and shorthand. So I'm going to jump straight in with the longhand. You can see here that we're following the pattern that we talked about in part 1. We've got 1s, 2s, 2p, 3s, 3p, 4s, 3D, and then we have 4p following on from there. It's possible to check your answers because you can see that, for example, silicon is a p block element, so it will end in p, and it's actually second as you go across the p block within its period. Oxygen is a p block, and it's 4 across. Calcium is in the second section of the S block, so it's on the right hand side, and iron is in the D block, and if you count from the left of the D block across to iron, it's the 6th. So the number tells us how far into the block we are, and the block tells us which the final sublevel will be. But then we need to look at the shorthand as well. Now, you might remember from previously that we look for the biggest noble gas that we can that precedes the element we're interested in. And I've put square brackets around the configuration of that noble gas. So I've got my 1s2, 2s2, 2p6, which represents neon, so I can cut my answer considerably shorter. My 1s2 is helium, and I can go from 1s2, 2s2, 2p6, 3s2, 3p6, and abbreviate the whole of that as argon. That then allows me to finish them in this way. So we're going to move on. I'm going to take a look at first ionization energy, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions with a +1 charge. You need to remember that, but you need to remember it with the confidence to use it. And it might be useful for you to actually pause to try the left-hand side of the screen and then double check you're on the right track. Okay, so you're asked for the first ionization energy of lithium. Well, you'll notice that I've got the lithium here, and there's 1 mole of it, so I don't put a number in front, but you'll also notice it's gaseous. Now, we don't generally think of metals being gaseous, but that's what the definition tells us. The definition also tells us that we're going to make 1 mole of gaseous ions with a +1 charge, and that's what we've got there. The state symbol is in, the charge is on there, and finally we do that by removing 1 mole of electrons. Hopefully the colour coding is helping you to see why we've got to the answer that we have. And just a reminder, I've highlighted it here, you need to learn this to get 1 or 2 marks, but you can then apply it to get many, many more. Try the rest of them, and then we can review. So pause and move on when you're ready. So in the first instance, we've got zinc. So we're going to go Zn to Zn plus E minus, but we haven't fulfilled the criteria of the definition because the definition tells us the atoms and ions are gaseous. So I put the state symbols in. When I look at calcium, I'm going to go from Ca gaseous to Ca plus gaseous and E minus. And we do the same thing with lead, Pb to Pb plus, and molybdenum, Mo to Mo plus. Now we can summarise that into a very neat little general equation. And that's where the element is X, and we have X, always gaseous, goes to X plus, always +1, always gaseous, and we always have an electron being lost on the right hand side. It goes against what you might have learned. Calcium forms ions commonly of +2. This is showing us part of the process by which that Ca +2 ion is formed. Okay, once we know what ionization energy is, we need to be able to recall and explain the trends. And you've been provided here with the trend going across period 3, Namgyal-Sipskar. What you need to look at with this is how would you describe the general trend? Remember, the general trend is what happens overall even though there might be one or two anomalies. And then we need to explain why that's the trend. And as you do more work on periodicity, you will get more and more familiar with some of the key ideas. Now, the general trend is a direct observation from the graph. It's an increase. It goes up from sodium to argon. Yes, there's a dip from magnesium to aluminium. Yes, there's a small dip from phosphorus to sulfur. But overall, it increases. Why does it increase? Well, there's two specific reasons that you need to be familiar with. Number one, there is an increased nuclear charge. As you go across, you're adding a proton each time. And that nuclear charge with those positive protons is going to have a tighter pull on the outer electrons. That means it's harder to lose them. What we also have is no increase in shielding. Shielding, as far as we're concerned, we're going to simplify slightly, but shielding is done by full principal energy levels. So in each case here, they've got the same amount of shielding. So because there's an increased nuclear charge holding on to those electrons tighter, but there's no increase in shielding pushing those electrons away, what we get is an overall increase in energy needed to remove the electrons. So let's have a look at what that looks like in specific examples. And we've got a blue box here that tells you how you might compare two neighbouring elements. And very, very often in an exam, you are comparing two neighbouring elements. Have a think about the examples on the right, see what you can remember, and we will review when you're ready to move on. Now, my big tip here, when you're comparing two, is to always write out the electron configurations of both of the elements. It might seem like it's a big impact on time, but it actually helps you to really strongly visualize what the differences are and therefore why we see what we see in terms of the trends. So aluminium and silicon end in P1 and P2 respectively. Now that means that we've got no difference in shielding, and we have got an increase in nuclear charge from aluminium to silicon. There's one more proton. So actually, the difference, we know it goes up from the graph. There's an increased nuclear charge, but there's no increase in shielding. The same as the explanation for the general trend. Now let's look at magnesium and aluminium. If I write these out, you can see that magnesium ends in 3s2 and aluminium ends in 3+1. Now don't fall into the trap of thinking that there is a different level of shielding. There is not. What there is, however, is in aluminium a higher energy sublevel. Now to get the marks you need to specify that sublevel. So you would say that in aluminium it's lower than magnesium because the electron is being removed from a higher energy, in this case 3p sublevel. Because it's higher energy, it means we need to put less in to remove the electron. And then finally, phosphorus to sulfur, we have got electron configurations 3p3 and 3p4. Now if you've watched part 1 of this topic walkthrough, you'll remember we spoke about the people on the bus and sharing in orbitals, and that's what this one is all about. So there's no difference in terms of energy of sublevels, there's no difference in shielding, there is an increased nuclear charge, and yet there's a dip to sulfur. So if I draw it out in this way, you can see that in S, we have two electrons sharing an orbital. In P, we don't. What we're looking for is that two electrons are now sharing a 3p orbital, and therefore, because those electrons repel each other, we need to put less energy in. So we're going to carry on building on this and forming a summary. The first ionization energy summary is very, very important because there are only 3 answers as you go across the period. The first one is the general trend, and any that go up can all be answered by answer A. Increased nuclear charge, no increase in shielding, so the energy, first ionization energy, goes up. For B, we have magnesium to aluminium, and that's because the electron is removed from a higher energy, P sublevel, so less energy is needed. And finally, just a repeat of what we saw just a moment ago, we have got 2 electrons sharing a p orbital. The electrons repel, so there's less energy. That gives you every answer that you might need for going across a period. In an exam, they might give you Liber-Birkenkopfni, lithium across to neon. The pattern follows in exactly the same way. The drops are in exactly the same places for exactly the same reasons. What we also need to do is have a look at what happens to first ionization energy as you go down a group. Have a go at these questions and see how you do. So electron configurations is a nice recap of information that we already have. 1s2, 2s2, magnesium ends in 3s2, calcium ends in 4s2. So they all end in s2. What we have got here is an extra principal energy level every single time. So why does it decrease as you go down the group? Well, we think about this logically. We relate this to the reactivity of group 1 that you've learnt about at GCSE. The outer electron is further from the nucleus. That means it's less attracted. It's also subject to more shielding by the inner electrons. For that reason, less energy is needed to be applied to remove the outer electron. And then we need to look at successive ionization energies. A really common question, something that comes up a lot, and a really lovely little 1 or 2 marker sometimes, as long as you are confident with what you need to do. So first ionization energy takes us from an atom to a +1 ion. What might we mean by subsequent ionization energies? First of all, do we now remember the definition for first ionization energy? The enthalpy change when 1 mole of gaseous atoms loses 1 mole of electrons to form 1 mole of gaseous ions with a +1 charge. There are some threads that you need to be familiar with going right through this. The 1 mole of atoms makes 1 mole of ions after losing 1 mole of electrons. Really important. But also the fact that the atoms are gaseous and the ions are gaseous is very, very important. So now let's go on and take a look at the potential second ionization energy of zinc. Have a go, work your way through, and then double check that you're on the right lines before you try the remaining examples. So what we're looking for here is a Zn plus ion, gaseous, goes on to become a Zn2 plus ion, gaseous, and it does that by losing an electron. Now the most common wrong answer is people jumping from Zn all the way to Zn2 plus, losing 2 electrons. What you've actually got there is the combination of the first ionization energy and the second ionization energy. So you've got to be very careful with that. With all of that in mind, try the remaining 3. And hopefully you're along the right lines. In second ionization energy, it's always a gaseous +1 ion going on to a gaseous +2 ion, losing an electron, and obviously scaling that up to molar quantities. But how are we actually going to address this within an exam? Well, let's take a look at magnesium. You've been provided with the first, second, and third ionization energy. So we can put the equations in. First takes us from Mg to Mg+, second, Mg+ to Mg2+, third, Mg2+ to Mg3+. What do we notice about where the big jump is? Well, let's actually add up those figures. We've gone from 738 to 1451. It's gone up by 813. Then we've had a massive jump of 6282 on the third ionization energy. The big jump is when the third electron is removed. We know that magnesium is in group 2, so the third electron is being taken from a lower principal energy level, which is closer to the nucleus, subject to less shielding. Of course, it's going to be much higher. Let's do the same thing with sodium, and we've got some questions here to work through, so have a go and see how you do. So the equations you can see here, Na to Na+, Na+, to Na2+, Na2+, to Na3+, all gaseous, all losing 1 mole of electrons. And the big jump here is actually between the first and the second. So the big jump is when the second electron is lost. Now let's look at the electron configuration of sodium. It ends in 3s1. So the first electron is lost from 3s1. But the next two are lost from 2p. We lose the 2p6 and we lose the 2p5. So we've got a massive jump when we move from the third principal energy level, 3s1, to the second principal energy level. And so because the big jump is after the first ionization energy and before the second, that gives us evidence that sodium is in group 1. So let's look at some exam questions now. What can we do with this? Have a go at these and then review your answers. So, in the first instance, we have got a period 2 element, and the period 2 is lithium across to neon, libobicanophony. We've got the successive ionization energies. What do we think is the identity of the element? Well, if we look at this, we can see the big jump is after the 4th electron has been removed, before the 5th electron is moved. That tells us it's group 4. Because it's period 2, I look at group 4 in period 2, that tells us it's carbon. On the next one, a slightly different way of dealing with it. We know it's magnesium, which is group 2, so we're expecting the bigger jump on the third ionization enthalpy. So I have got my magnesium, I lose 1 electron, I lose a second electron, my third electron is lost from a lower principal energy level. So I'm going to expect it to be a bigger jump. I'm going to expect it to be closer to 4th than 2nd. I've gone for about 7,000 because then we're going up by around 3,000 each time here. And finally, on this section, we have got the table with successive ionization enthalpies. What group do we think it's in? Well, we've gone up by about 500, then we've gone up by almost 4,000, then 1,500, then 1,700. The biggest jump is after the second electron has been removed, which tells us it's group 2. That takes us to the end of this section. Part 3 will introduce mass spectrometry. Thank you for listening.